Hello, everyone. This is our last lecture of this course, Information Theory. And it's not will be a full-blown lecture. It will rather be an epilogue, which normally is called take-home lesson. But I would rather call it take to the lab lesson. I'll try to compress, in the spirit of this course, code in the most efficient code, what I suppose that you can take with you to your own research, to the lab, to your office, to the library, where you can use it as a tool. And it's all about what can we say, do, learn, or transfer about things that we know only partially. And as we discussed, the most simple and yet powerful approach is phenomenological, and it's called thermodynamics. And when you'll be doing thermodynamics, namely phenomenological description of a cell, stock market, informational system, society, anything, you'll start from identifying things which are conserved in some sense. So when I give you, I have less and you have more, and we call such things energy. And you will be trying to identify a second thing which is growing on average, and it is called entropy. And they are both extensive things. And generally, for arbitrary system and arbitrary state, there could be any energy for any entropy. There is nothing particularly relating them unless we leave the system to equilibrate either alone or in a contact with some other large big system that provides whatever interaction it is. And in this case, there is a unique relation, equilibrium relation, between entropy and energy. And because entropy reaches its maximum in equilibrium, this equilibrium relation denotes the upper bound of the region. So all available states are here. And this is equilibrium, and this is all non-equilibrium states. Now, system can equilibrate, reaching some point at equilibrium by a growing entropy at a finite energy, or decreasing energy under a finite entropy, which means that this equilibrium is under certain condition is a minimum of energy, or it can reach this point by any other trajectory. And there is a very interesting subject of how actually this is reached but its important message here is that entropy growing, and it's all started, as we discussed, from a very basic question, was about engines efficiency. And engine, thermal engine in its simplest manifestation, and I really want you to remember this simple diagram because it's extremely helpful and powerful in many things despite its extreme triviality. So you have a reservoir with a high temperature. You take some heat Q1 out of this reservoir. There is another reservoir with low temperature T2, and you deliver some heat Q2 to this system, and then there is some difference which you can use, and for example, to do work. And when you are designing engine, or it could be anything, that could be what you gain out of your market transactions. This is something which you can measure and which is useful, and then you ask what is the ratio of the heat that you taken that you can use, and this is called engine efficiency, and apparently that this is Q1 minus Q2 divided by Q1, or this is 1 minus Q2 divided by Q1, but you can replace it by T1 S1, and this is by T2 S2, and this is by T1 S1. And so you defined temperature as a derivative of energy with respect to entropy. And it is the convexity of this curve which allows you to describe, to introduce temperature for any point, which means the derivative always changes in the convex curve. It could even go down. There are systems which it does, but what is important is that it's convex, so you can introduce temperature, and because you say that S2 is always larger than S1, then this gives you an inequality on engine efficiency. So you say that the engine efficiency is bounded by this, and this is how all the science started. Essentially, what we were doing for the last 200 years is applying this type of reasoning from engines to communications, and then to computing, and then we start applying it to thinking, and at some point we probably will apply it to feeling, or we do it for some other activities. But essentially, this is on this phenomenological level, just a statement that something is conserved, Q1 plus W is equal to Q2, and something grows, or at least non-decreasing. It's really very powerful framework in which you can then build your own application where what is energy is not really energy. It could be money, it could be some other biological function. And yet another thing, which is how you actually reach equilibrium, and it in thermodynamics is just one of the potentials, thermodynamic potential, which determines the system, and it's called free energy. And it's you can apply it anywhere, but it's particularly useful when your system is attached to a thermostat, which keeps a finite temperature. So the free energy, as physicists very much like, contains two terms, and it describes their competition. So your equilibrium state, and again, under finite temperature, is a state of a minimum free energy. And you can reach minimum of free energy either decreasing energy, which often requires some kind of ordering in a system. You want to put attracting parts close to each other. You want to put repelling parts farther away from each other so that they interact more weakly. So that way you arrange your system in some ordered way and lower energy. But it works when temperature is low enough, and you can essentially disregard this term. But if temperature is large enough, then there is another way to minimize your free energy. It's a way to increase entropy, and this requires increasing disorder. And this is the way that phase transition happen, and not only in physical system where something boils or system loses its magnetism or whatever. It happens also when computer algorithms work, and when you change parameters, it suddenly comes into a new regime, because essentially this parameter negotiates this balance between two things. And as we discover over and over again, it's something which most of information processing and engineering actually does. So we used to think about it, saying that what we can use for work is not the whole energy, but it's something less, because I need to keep temperature. I am at a finite temperature. But there is another perspective, informational perspective on it, which says that this is entropy. This is essentially your measure of what you don't know about the system. Entropy is not a property of a system. It's something which characterizes our relations to the system, how much we don't know. The more we do not know about the system, the more is entropy, the less energy we can use. Of course, you can say that this is my money and this is my knowledge of the market. The less knowledge of the market I have, the less effectively I can use my money. It's a very, very powerful framework, and even though it's pretty simple and straightforward, it really gives a lot of results. Now, on the next level, when we go down from this, we use statistical approach. Namely, we try to explicitly quantify how much we actually do not know about the system. And for this, the simplest things that we need to know about system is just the total number of states, what R could be. For example, we don't know anything, but at least we know what are possible states of it, and that was a huge step of Boltzmann, we say that the entropy is essentially logarithm of this, which is traditionally called gamma by Greek gamma, but it is essentially a number of states. And if we don't know anything about the states, we assume that the system could be with equal probability in any of such states. And it is then possible to prove that this is the maximal entropy state. And this is just minus a logarithm of, I'll be using logarithm because everything will be in bits, so it will be log by 2. So it's 1 divided by probability be it any state. And then it's without minus. On the other hand, if we know something about different probabilities, namely those are numbers which are not equal to one another, then we generalize it for a Gibbs probability, namely what we take an average logarithm, and this is S. Okay, and at that point, I really want to stress two very simple mathematical ideas which are used over and over and over again in this course. And one of these very powerful mathematical idea is the idea of convexity. That first of all, that when you have a convex boundary of the domain, that your extrema usually lie at the end of the boundary. But we also use this convexity in a very creative way when we describe the exponential separation of trajectories and entropy growth in a dynamical way, or in some other way, we use the convexity of exponential function. So if we have x, and this is exponent of x, and on average x, let's say with equal probability, changes in some interval, so that the mean value of x is equal to 0, it's straightforward, just visible from the convexity of this exponent, that this is larger than 0. So if on average my x, which could be expansion or contraction, so these rates are on average balanced, overall the exponential of it will be net stretching or net separation, and that's how the idea of dynamical chaos is born. But on the other hand, we use the convexity, this simple, very, very intuitive picture of convexity of exponential function in a very creative way, because when we proved the modern form of the second law of thermodynamics, it is not inequality, it is equality. It's a statement that if you have different realization, different trajectory, and each one is characterized by its own entropy change, and these changes could be positive and they could be negative, if you weight this trajectory by the exponent of this change, which is essentially your phase volume, you would get on average unity. It's a very powerful statement, but it immediately follows from here. So if the average of the exponent is unity, it means that this interval is shifted somewhere to the left. It means that minus delta S on average, it's less than 0, which essentially tells you that delta S on average is non-negative. And this is the old undergraduate version of second law of thermodynamics, which we used before. And the second, this was the first mathematical idea which we used over and over in the course. It was convexity. And the second very simple mathematical idea, which again we used over and over again, it's essentially the law of large numbers. And it tells you that if you just sum some numbers, then this quantity very fast up to 1 to n, then this quantity very fast approach just the mean value times n with exponential accuracy. And of course, there are more sophisticated forms of it. Then you say that the fluctuation around this mean value have a Gaussian form, which is called central limit theorem. And then you can even describe distant tails by large deviation theory. But already in this form, it is extremely useful relation, in particularly when we apply it to a probability itself. For example, if we have a sequence of symbols, letters, data, and it's long enough, we ask the question, what is the probability of this particular sequence? The only thing that we know about it is that these things are randomly somehow chosen and they are statistically independent. But then we can say that if we look at the probability of such a sequence and we take a log of it and we take limit when n going to infinity, first of all, those are products of probability of different things. So the logarithm is the sum of random numbers. So it asymptotically approaches n and the mean value of a logarithm, which is entropy according to this formula. And it is essentially tells you the following with a sign minus. It is what is formulated in a very neat and memorable way, as almost all events are almost equally probable. It is a statement, and it brings this idea of a typical sequence. It says that if this, in the limit of n going to infinity, we are more and more likely with exponential, with probability which exponentially goes close to unity, to see a sequence which is typical, and all these sequences have the same probability. Okay? And this powerful idea then expressed in the information theory, because it says, for example, if you have this sequence, it's just in a binary code, so you set some zeros and ones, and you would like to know, is this the best encoding? In general, if you have n such symbols, then there is 2 to n binary sequences of such lengths. But as it's easy to show that the entropy of a binary is minus p log p minus 1 minus p log 1 minus p, and this is strictly equal than 1, and it's equal to 1 again by convexity only when p is 1/2. When zeros and ones, which tells you that 2 in the power s is less generally than this. So you don't need this encoding. You can use more effective encoding, which will be encoding only typical sequences, and this is why entropy plays such a prominent role in information theory. It's because it describes not only average rate of information transfer, it also describes ultimate rate, the fastest rate of information transfer, or the shortest mean lengths of the code word which you use to code your object. And so it is this simple idea, which sometimes is called asymptotic equipartition, and of course which physicists and mathematicians and economists used over and over again, sometimes using different names, but it's essentially this idea of typicality. And after that, again, within the information theory, we went next step and tried to understand what would be the entropy of the most familiar to us mode of conveying messages is a language. And we understood that in this case, just knowing the probabilities of letters is not enough, because letters are correlated. After Q, it's always U in the English language. There is no independent probabilities in this case. And it brought us naturally to considering conditional probability, let's say, of y plus 1 under condition of yi. And of course, in the language, there are even 3-letter and 4-letter probabilities. Another thing, so the real entropy of a language is much less than single-letter probability would tell. But this conditional probability turned to be extremely important and very general, because what it allowed us is to consider a very general framework about messages, measurements, memory retrieval. We obtain A, which could be a result of a measurement, which could be a message, which could be a memory. But we really want to know A. Okay? And if this is exactly equal to that, there is no problem. But generally, there is something remaining. And it is this conditional probability is exactly what determines the correction between B and A. So what is the probability of having B if we are given this value of A, for example, Bi on Ij? And so it is this conditional probability which introduces a very powerful quantity and formalism, which is based on this notion. So we can say that after I obtain A, there is still some remaining uncertainty about B, which is S of AB. That was my uncertainty about both A and B, and minus I remove the uncertainty of A. Now I may ask how much this measurement, this message brought me, and of course brought me about B. And I can say that I had before uncertainty about B characterized by the entropy of B, and now I have this. So the difference is essentially what brought the message, and then I see that this is the following thing: S of A plus S of B minus S of A and B. And this is called mutual information between A and B. And this mutual information is something which tells me what is the degree of correlation between A and B. And there is another very important, I believe, technical message here, particularly for physicists, because physicists used to characterize correlation by correlation function, by something like A times B taken on average. This is a good measure of correlation only when statistics of A and B are Gaussian. This is a universal measure of correlation for whatever statistics it is. And I think that this simple technical knowledge has not penetrated enough into physics community. But even more important is a conceptual consequence of it. Because now, by using this, we can return back to our statistical consideration of entropy, and we understand better the old paradox related to Boltzmann equation. If we consider particles with a momenta and with a coordinate, then we can show that the entropy of this old distribution of n particle interacted by some interaction Hamiltonian is an integral of motion. It's conserved. It does not change. On the other hand, what Boltzmann showed that if you consider a single particle and you consider momentum of this particle, let's call it P1, and you have a probability distribution of it, in equilibrium it will be some kind of Maxwell distribution at a given temperature, but generally it could be any distribution. What Boltzmann showed is this quantity grows, which means that if I really look at entropy as an additive extensive variable, and I assume that my particles were initially all correlated, that the entropy was just the sum over I of entropies of all these particles, and this is growth, and this is not. And then we understand that if we look at it, if we take this and subtract the whole probability, the whole entropy, what we get a mutual information between all the particles. And this is precisely what happens when you start from uncorrelated state and you let particle interact. the single particle entropies would grow, the total entropy would stay, and the correlation between them increases. So in a sense, this is, again, the new way of looking into second law of thermodynamics is not saying that those quantities are growing, but saying that those quantities are conserved. They are essentially equivalent. Or by saying even more meaningful statement that the mutual information increases. And this example in particular shows you how partial knowledge, when we focus only on one particle, make entropy grow. But then we discussed that there is another way of entropy growing in a physical system, and it's the way when we have a finite precision. So if in this multidimensional phase space, and this is just projection on a single particle, but imagine that there is a multidimensional space, our precision is, shall we stop it? The record was stopped, so give me a sign when I continue. Okay, so if our precision in this phase space is finite, namely, we do not know exactly the coordinates and the momenta of our particle, the evolution with time will be this Hamiltonian evolution, which is incompressible flow, so it would stretch in some direction and contract in another direction, so that the total phase volume is conserved, but our precision still remains the same, so we'll perceive it as a growth of a phase volume. That's what we'll be perceiving, and this is another mechanism of entropy growth, which is again based on the partial knowledge, and this is a mechanism of a dynamical chaos. And again, it is in this mechanism that we argued the average growth of a phase volume, even assuming that on average our rates could be both positive and negative. So this is more or less how this information theory approach gave us a very new and, in a sense, trivializing way of looking into our paradoxes of statistical physics, which are just now turned to be very, very natural statement about the fact that if you don't know something, then your information that you do know is getting less and less relevant because there appears more and more correlations. And then when we went to the quantum information, we see that on the way of entanglement. We take a quantum system and attach it to a big system. And even if they together could be in a pure state, just the interaction means that the information about the small system will be encoded further and further away into the big system, and that would mean that effective entropy or our uncertainty about a small system would grow. So this was a very natural framework, but there is yet another technical, very important thing that we need to take out of this quantity, and this is something which any experimentalist need to know, and this is called bias formula, or which I would rather call a bias framework of thinking. And it tells you that the probability of this hypothesis to be true under condition of a given evidence could be computing, because what you need to take a prior probability of this hypothesis to be true without any evidence and multiply it by this factor, which is the probability of this evidence under this hypothesis being true, divided by the probability of this evidence. This is a very important formula. First of all, technically, there are so many false statements made under the pretense of statistical validity in the literature, which literally do not use or abuse this formula. But there is also conceptual importance here, which I think that physicists resisted long enough, and we need to accept it, is that there is no inference without prior assumption. This is very important. And we used to be blind, not only in our private lives, but also in our professional work. We often used to be blind to all the implicit and prior assumptions that we made, and Bayes' formula actually focuses on it. And it's particularly fascinating to see now application of this formula taken together with this very powerful approach of a free energy when we apply it to economical, social, and psychological events, and particularly active inference by our mind, which tries to, again, to negotiate some balance between what it observes, namely what sensory information it receives, and what its prior beliefs and assumption. And maybe the last thing that I want to call your attention is that so much in all this framework hangs on getting the right conditional probability or just the right probability, that it's a most natural task which experimentalists face in the lab or theoreticians face at their writing table is the task to find a distribution. So how to find a distribution in the right way, it's something which needs to be done within the same framework. And again, I want you to remember this sentence that your distribution must contain the truth and nothing but the truth. This is very important. The truth is the data. That whatever you have data, your equations of motion or of evolution that you are sure about, and it's usually only partial. And this statement means maximal entropy, which means that your distribution, your outcome, your hypothesis must contain only this data and maximize your possible uncertainty about events. It should not include anything which is the truth that you're absolutely sure. And as you've seen technically, it usually means that the probabilities somehow have an exponential form, and here is more or less your data over here. Again, we used to think in physics that the maximum of entropy under given condition is a property of thermal equilibrium. What this shows here, no, it's a totally universal approach. It works describing the statistics of neuron firing, and we are definitely not in thermal equilibrium because otherwise we will be dead. We are very much alive, and yet our neurons firing in the brain could be described, their statistics, just by using the data about mean values and correlation and take an exponent of this data. And this is a very, very powerful general framework which works everywhere, and we need to be aware of it. And maybe the last, and this is particularly physicist thing, but it's getting more and more important all over, and now everyone tries to learn it, is a renormalization group as a right way to forget. Because what is about information is that not that we only are interested in how to get it, or how to transfer it, or how to compute using this information, we are also devised a very effective procedure of forgetting, which means that we try to erase some details of the system, simultaneously renormalizing the parameters of the remaining degrees of freedom which we continue track of it. It happened to be, if properly made, a very powerful procedure because it will be focused not on a distribution, this or that distribution. It is focused on the families of distribution which under this action of this transformation, which is not even a group, it's semi-group, but it's a flow. So what you do, you average coarse grain of a certain parameters, you change your distribution, but then you change your parameter. Under this change, your distribution flow to some ultimate universal fixed point distribution. So this is again a change of focus from particular distribution to classes of distribution and the evolution of distribution under this form. And it's again not only very technical and conceptual tool. And the last lecture in the course, the previous lecture, was about quantum information, where I believe maybe the main thing to take home is the idea of entanglement. That when you consider a given, and it could be not necessarily restricted to the quantum world. It will be a much more powerful idea, maybe in some other things, that when you consider look at a given system, your entropy could be large because there is some information about the system which is outside of it, which is in the outside world. So that's more or less what this course was about. There were definitely, you notice that there were practically no rigorous derivation, and you can find them in the book. You can find lecture notes at my webpage at the Weizmann Institute, and it's constantly updated, and hopefully next year it turned into a book, but so far you can find more or less a constantly updated version at the front wave page under the lecture notes of information. Again, I would like to say that I did not touch in this course a very important notion of complexity, because more or less it was a physicist and engineer's approach towards what works on average. And it's a very interesting idea of Kolmogorov that you could be interested on what is a minimal description. If you look at a given sequence, you may, of course, assume that it's a typical sequence like this y1, yn, but you may ask what for a given system could be the shortest encoding of the system. And it could be really complex, namely that its encoding is its sequence itself, or it could be relatively simple. A system which could be encoded much shorter. So this idea of complexity is usually taken in mathematical courses, and it's not here. And again, numerous applications you can find in several books. And now I want to thank you for your patience during this course. Thank you very much. That's the end of it.